Um, is it recorded? Okay, good. Okay. Good morning, everyone, for joining for this distinguished webinar series in AI and cybersecurity. Today's speaker is Dr. Daniel Henderson, Professor of Economics at University of Alabama. The title for today's talk is Unifying Estimation and Inference for Linear Regression with stationary and integrated or near integrated variables. Dr. Henderson is a professor of economics and the J. Weldon and Delores Cole Faculty Fellow at the University of Alabama, as well as a research fellow at the Institute for the Study of Labor in Bonn, Germany. He was formerly an associate and assistant professor of economics at the State University of New York at Binghamton. He has held visiting appointments at the University Catholique or Institute of Statistics in Belgium, Research Foundation Brussels, School of Mathematical Sciences in Nankai University in China. There are many other places in China that he has served in different roles, and I think you can read from the flyer. He received his PhD in economics from the University of California, Riverside in 2003, and his BA in economics from the University of California, Davis in 1998. His research primarily focuses in applied non-parametric microeconometrics with an emphasis in the economics of education. He has also written papers examining the determinants of child health, economic growth and development, environmental economics, and international trade. His work has been published in journals such as Computational Statistics and Data Analysis, Economic Journal, Economics of Education Review, European Economic Review, International Economic Review, Journal of Applied Econometrics, Journal of Business and Economic Statistics, and Journal of and several other journals. I think it's quite a list to read. And in addition to many subfields of economics, his work has been cited in the fields of accounting, archaeology, biology, earth science, education, engineering, environment, forestry, geography, geology, geoscience, neuroscience, operational research, etc. His research has been featured in local, national, and international newspapers, magazines, and blogs, including several newspapers, Boston Globe, Chronicle of Higher Education, and Sunday Telegraph magazines, Atlantic Monthly, Business Week Online, and US News, and several other blogs. Dr. Henderson, it's a great privilege to have you and host you as part of the webinar series at the University of North Dakota. Thank you so much for agreeing for this particular webinar, and the floor is yours.
All right, thanks a lot. It always sounds exciting when somebody else says what's been done. So let me share my screen, and then I'll do my generic talk about what the paper's about. But I want to start a little bit about...
Yeah, very good. We can see your screen.
Okay,
yeah.
Perfect. So this is a talk on artificial intelligence and cybersecurity, and I am...
We can't hear you. Something happened?
Oh, you can't?
I'm able to hear you.
Jameson, can you hear?
Yes.
Okay, I can... Okay.
Dr. Henderson, are you speaking?
Yes, I am. Is anybody else having trouble with this?
Yeah, I think we can hear you. Yeah, sorry.
Okay, that's fine. Okay, it looks like at least a certain percentage can hear. All right, so let me try to we talked about all these, or there was some mention on the different fields that my research is cited in. And what's funny is that you study a particular problem, and when you're doing statistics, you don't really have an idea of where else it can work. And it turns out that it works in a variety of areas. So when I was asked to do something, give this talk on artificial intelligence, my default thought was, well, I don't do that. And then I thought, well, I also don't do neurology. I also don't do earth science. But it turns out that a lot of these math problems are very useful in other fields. And so I thought about this a little bit, and when I thought about what paper to present, I thought this one would be the best. So I studied time series for a very long time. When I was an undergraduate, I was studying it in statistics at Davis, and then when I moved to Riverside for graduate school, I studied a lot of time series. And then at some point I thought data was getting bigger, so I switched to panel data methods. So repeat and measure type problems. But I had always kept teaching and kept studying time series. And what it took is Jiancheng Zhang is, he and I overlapped when I was at Nankai. And so he kept coming to me with time series papers, and I thought, I don't really do these things, I just study them. And he finally presented me with an idea that I found very interesting. And sort of the basic idea is the following, that there are a lot of decisions we have to make as academics when conducting a study, and some of these are testable. But even things that are testable are not guaranteed. We're all very familiar with the failure to reject a null hypothesis is not the same as an acceptance of a null. And that's really what this paper is sort of about, is that there are many scenarios, and I'll go over a handful of them in a little bit in economics, where we're really not sure whether or not the process contains a unit root, whether or not it's integrated. And so we have formal tests, Dickey-Fuller and things like this. But there are some times where these coefficients are, I don't want to say dangerously close to one, but very close to one, such that we cannot distinguish them. And so if we start relying on computers to pick a path, it's going to pick one path or another, say something's a unit root or not, and then continue to conduct research along that line. And so we're losing a little bit of the economic thought, but even if we have economic thought, we may be wrong. And so what we're really trying to do in this particular paper is say, look, we don't know whether a process is I1 or I0, because it may be nearly integrated, a coefficient very close to 1. And so what we're going to try to do is step back and say, look, I can test these, but I'm not sure whether a failure to reject a null is the same as a rejection, is the same as an acceptance. And therefore, can we find methods to where we don't have to make a decision? Can we find methods where we hope to be able to do some sort of predictability, but not have to predefine whether or not a variable is stationary or non-stationary? So that's sort of what we're doing here. We're going to find some unifying approach where we have state variables that are going to be either I1, I0, or nearly I1. And we're not going to have to decide. We're just going to develop the estimation method, which they will all have the same asymptotic distribution, because we know that in most cases they have different asymptotic distribution. And therefore inference is going to be tricky because we have to know this beforehand. And if you pick the wrong one, then inference will be incorrect. Now, what we're going to do is we're going to apply this to asset pricing models and see if we can predict on excess stock returns, which if we're right, then we should be millionaires at some point. I'm an academic, so I'll probably let somebody else make the money, but that's what's happening here. So this is co-authored with 3 statisticians and myself. The diagonals are in mainland China, and the off diagonals here are in the US. I am at the University of Alabama, as we said. All right, so let's sort of jump into it. I got a lot of slides, but I'll try to just give the basics here. So we're trying to develop a unifying inference and estimation procedure. We're going to use something known as weighted estimation. I'll talk about that in a little bit. Essentially, we're going to weight observations differently. So instead of everything being one by the sample size, we're going to give different weights to different observations. We're going to develop all the asymptotics for these particular estimators. And then we're going to also have to introduce a random weighting bootstrap method. So we're going to have a second set of weights in the bootstrap procedure so that we can calculate standard errors and whatnot. We show that the proposed method actually works really well. It outperforms the existing methods in the literature. And specifically, we can do this whether or not the errors are homoscedastic. So we can allow for heteroscedasticity, which is the norm, not the exception in economics. As I mentioned before, we're going to study the predictability of asset returns. And we're going to allow where some of our state variables are endogenous. So endogenous is a very economic term, which is just saying that there exists some correlation between our state variable and the error term. Typically, we think about this as omitted variable bias in statistics. All right, so I'm going to, like I mentioned earlier, I'm going to state all this very generically. There's going to be a bit of hand waving. There's theorems and proofs and whatnot. You're welcome to get a copy of the paper. If it's not already posted, I can send out copies of the paper. But what we're interested in is, so for the example, think about the left-hand side variable being excess stock returns. So this is the additional return you get over what you would get from a risk-free asset. Think something like a treasury bond. And we want to see if they're determined by a set of regressors. So these are what are known as our state variables. So you can think of book to market ratio or one of these common uses in finance. And that's going to be our X. And our X variable is going to be a AR1 type model. So we have an autoregressive model for the right-hand side variable, and we want to know whether or not they're stationary or non-stationary. So in the case of a single variable, it's going to be stationary if the rho is less than 1 in absolute value, right? Now, for simplicity, I'm going to do everything for rho being positive, so I'm not really going to talk about the absolute value, but it needs to go between -1 and 1. We're going to focus on rho being positive, but it's analogous for negative values of rho. All right, so T is going to be our time index. N is going to be our sample size. U is going to be a noise term. You can think about this being an IID normal. You can think about it being some sort of stationary white noise process. We're not going to get too much into those details today, but we are going to assume here that XT minus 1 and UT are uncorrelated. That assumption we're going to make. All right. Now, as we mentioned before, if rho is less than 1, this is a stationary process, what we refer to as mean reverting. If XT is stationary, then a regression of YT on XT, we just use least squares, and we get the standard sort of root n consistent estimators, asymptotically normal. This is what we learn in introductory statistics. All right, now if rho is equal to 1, or -1, of course, then we have a non-stationary process. This is known as the unit root process. In the example we showed before without an intercept, this is known as a random walk. Now, most economists will tell you that stocks follow a random walk, meaning they aren't really predictable, that XT is just simply a function of XT minus 1. If you have rho greater than 1, then this is an explosive process. The examples they used when I studied statistics at Davis were in entomology with the reproductive habits of insects, which kind of grossed me out. Where it happens in economics is we're going to be in cases where rho is just slightly bigger than 1. This is going to be really common. So pricing bubbles, so housing bubbles and things like that are believed to be associated with rho that's very close to 1, but slightly above. So these would be explosive processes. Now, if rho is sufficiently far from 1, say 1/2 or 1.5, it's relatively easy to say, okay, this is stationary or this is non-stationary. And if it's stationary, just run a regression. If it's non-stationary, well, we know what to do then, especially if rho is equal to 1, then we take first differences, for example. However, when rho is very close to 1, we don't really know. And so and remember, failure to reject a null is not the same as an acceptance. Now, there's a lot of examples where this holds true. There's a lot of debates in economics, and there'll be these back and forth where people go after one another. For example, the unemployment rate. So historically, we talked about, if you think of the Milton Friedman sort of sense, there's some natural rate of unemployment. So Friedman never really said the exact percentage, but something like 2% or 4% people naturally lose jobs and gain jobs. And you think about the unemployment rate being stationary, just more or less constant. It bounces a little bit, but it always seems to mean revert. Now, there's other studies which talk about this hysteresis hypothesis. And the idea is that if you become unemployed, think about there being a big shock, that unemployment sort of hangs around because you've lost experience, and you've unemployed for a while, you may be unemployed for longer. And so they may show that it's I1. And in the literature, they've been showing both forms, right? So it's estimated back and forth. So some people say I0, some people say I1. Other examples are inflation. So in inflation, stationary prices are required for what's known as sticky price models. I've read a bunch of these, and it seems like even within a study, we don't know whether they're I0 or I1. Similar results happen for exchange rates. And these are very important because they will talk about whether something's I1 or I0 will have big impacts on policy. So the purchasing power parity is one well-known example. Sometimes the economists will talk about the Big Mac index and things like this. Okay, now, asset prices are also a case where there's a debate whether or not stock prices follow random walk. So there was a famous book called The Random Walk Down Wall Street. And then there's a follow-up, Not a Random Walk. And so there's a lot of debate on this. Most economists will believe an efficient market hypothesis, which suggests that everything that's known about a stock is already in the stock price, and therefore there's no predictability without, say, some insider information. Now, the finance literature has found a lot of puzzles where stocks appear to be predictable, and that's the application we're going to do. It turns out that we find that in certain years, certain variables do appear to predict stock prices. And so if this is true, then there's some money to be made. All right. Now, what we're really going to be, sort of considering is these near integrated processes where a coefficient just slightly above 1 or just slightly below 0. Those are going to be harder to predict. And so we're going to try to find a method that does not require us defining that in advance. All right. So it's going to be the case we have multiple x's on the right-hand side. We may or may not know the orders of integration, or they may be differing. We can either sort of make these assumptions and transform variables as needed, or we're going to switch to some method that does not require us to pick the order of integration. And this is the sort of approach we want to do, because if we're thinking about having computers do this for us, the computer is going to do its best, but is still being forced to make this decision that it really shouldn't be making. All right. So let's think about this in a more formal setting. So our goal is to predict on Y. And what we're going to use, we're going to use state variables X. So Y is, say, the excess return for a stock. The X's are different variables. Think about typical stock characteristics, book to market ratio, price earnings ratio, and I'll talk about these a little bit more, but these are predictors. And the idea is that if any of the betas associated with these X's are significantly different from 0, then that would say that that particular X can predict Y, right? So beta is going to be our object of interest. We're going to want to estimate it and conduct inference. Specifically, we're going to try to estimate it consistently and then conduct confidence bounds. And if those confidence bounds do not contain the value 0, then we say that they are significant, and hence they can predict. All right. Now, we sort of mentioned this before, but X can be a vector of k different variables. Some are maybe stationary, non-stationary. Those that are non-stationary, we're going to use rho sub I, and I is going to be the ith regressor. If gamma I is equal to 0 here, then we have an I1 process, specifically a random walk. If gamma I is slightly less than 0, then we would have a rho which is slightly less than 1. So we would call this slightly stationary, very close. Remember, when you run like just a typical regression on an I1 variable, that coefficient is usually something like 0.99. Now, that could be I1, or it could be something close to 1, and it's hard to distinguish those two. When gamma I is slightly positive, then we call this nearly I1, but this is slightly explosive. So a value of rho like 1.01, right? And we said this is believed to be what housing bubbles look something like this. All right. Let's start off with OLS. So without any extra knowledge on what the order of integration of the x's are, we can run OLS. And OLS is just minimizing the residual sum of squares, right? So that's our V. So this is just simply minimizing VT hat square, right? T equal 1 to n. So that's just OLS. We all know OLS. This is our standard least square estimator for beta hat. What is this? In linear algebra, this would be X transpose X inverse, X transpose Y. Right, so this would just be a typical approach. I'm doing things here in summations to be consistent with the paper. So this is OLS. Now, if the vector of xt is stationary, then we know beta hat is root n consistent and asymptotically normal. This is just standard OLS. Now, when xt is I1 or nearly I1, we say that beta hat is n consistent. So it's sometimes referred to this as super consistent. And there's some old work by Peter Phillips, which shows that this follows a mixed normal distribution, which is a little more complicated to show. But if you were trying to use the critical values for a standard normal when it's really mixed normal, you may be making incorrect inference, right? That's the main point. So in the OLS setting, what we really should be doing is think like a Box-Jenkins approach almost. You would look at the order integration of X. So you'd plot the data, see whether or not it appears non-stationary. If it does, then you conduct, say, a Dickey-Fuller test. If it's I1, you take a first difference and then you put it. Okay, so that's what we teach our undergrads. My undergrads have an exam tomorrow on exactly this. And so this is what we would tell them, but what if we don't know? What if it's really close, right? And so if we're wrong, then we're going to be using the wrong critical values, right? Okay, so here's what we suggest. We're using something known as weighted score estimation. And it's going to look a little bit tricky, but the main thing here is we have this matrix, diagonal matrix omega. And omega t is going to assign different weights. And specifically, what's really happening here is we're going to downweight some observations that are too big, right? So typically, you would think each weight to each observation would be equal to 1 by n. That's equal weight. This is a weighted least squares type problem, where the weights are going to be downweighting some of these contributions to the score. And what this allows us to do is this allows us to get estimators that are all the same rate of consistency, right? So it turns out estimation is really trivial because this is just weighted least squares. So when we learned weighted least squares in linear algebra, what was it? It was X transpose W, where the weight, X inverse, X transpose W times Y, right? And so this is the same exact thing. It's just these weights, it's going to take a little while to digest it, but essentially what we're saying is we're trying to, weigh down some of these really big results. And this comes from the non-stationarity, right? So we're going to try to downweigh these in a little bit. But the estimator here is just weighted least squares, right? And we all learn weighted least squares. It's just being applied a little bit differently. All right. So what's nice here is that the convergence rate of beta hat weighted is the same as the convergence rate for beta hat. This estimator is asymptotically unbiased, normally distributed. We can construct wall-type confidence regions. This is an interval since it's for a single parameter, but we can do it for the whole vector W or beta. And you would be able to get the estimate of this from the ith diagonal element of the variance covariance matrix. The problem here is estimating like sigma square V, because we may have non-stationary data, right? If everything's stationary, this works out fine. If we have something non-stationary, then we have a bit of a problem. All right, so sigma squared V becomes a problem. And standard bootstrap procedures are not going to work. So if you think about a non-parametric bootstrap, what do? You take the residuals, you add them to the fitted values, and you get new y's, right? But we know if we have non-stationary data, that's not going to work. So what do we need to do? A block bootstrap, or there may be other methods. But we're trying not to make decisions about whether or not something's I0 or I1 or near I1. And so we're going to come up with a different procedure where we're going to shock the score function. So we're going to have a different set of weights that is going to allow us to reproduce the parameter estimates and still get the same distributions of the variance-covariance matrix. All right, so this approach is going to be robust to this misspecification. It's also going to allow for heteroscedasticity. And it turns out to be a really simple idea. So what do I tell my undergrads all the time? I said, when we get stuck in math, we do one of two things. We either add 0 or we multiply by 1. And what we're doing here is essentially multiplying by 1. All right, so what we're going to take is we had that score equation before, but now we're multiplying by another weight. We're going to multiply by some random variable that comes from a distribution with mean and variance equal to 1, right? So the mean and variance of this term is equal to 1. So you can think about a normal 1, 1, or an exponential with mean and variance equal to 1. So all we're really doing is multiplying by 1. We didn't change anything. But what we did is we just, shimmy it a little bit. And so we can still get variation in beta. So we're not reconstructing the y's because we don't want to use those residuals for variables that are I1. Okay. All right, so it turns out that you're just going to multiply by this additional weight, right, or this additional shock, and then the estimation looks almost identical. It's weighted least squares again, we just have two different terms, right? So it turns out to be very straightforward. It's still a least squares problem, right? And this is the estimator that we get out of that. And the idea is we're going to look at the relationship between beta hat star W and beta hat W, and we can show, or we show in the paper, that distribution is the same as the distribution between beta hat and beta, right? The difference between those two particular terms. And so in doing this bootstrap, we're going to get the same sampling distribution, therefore we can conduct inference. All right, so how do we do this? I simplified it down a little bit. It's in the paper, and I forget which particular section. So what we're going to do is we're going to use the original sample of y and x to estimate beta hat W. And then we're going to draw these draws from a distribution with mean and variance equal to 1. Think normal 1, 1. Then we're going to calculate beta hat W. Then we're going to repeat this, I don't know, 1,000 times, right? And then we're going to use this bootstrap sample to construct the confidence regions. So that's the basic idea here. All right, so I'll probably go through this relatively quickly, but we're going to run 1,000 simulations. And in each one of those simulations, we have to draw 1,000 bootstraps. So this is going to take a little bit of time. All right, so we're going to construct a setting where we have, what do we have here? We have a constant term, and then we have 4 different regressors. The first regressor is going to be stationary. This is going to follow a random walk. This is going to be explosive. And this is also going to be a unit root, but a negative coefficient here. Oh, sorry. I messed that up. These are the betas. These are the betas here. These are the rows. So we have a non-stationary term, a unit root, and then 2 nearly integrated processes. So x1 and x1 is I0, x2 is I1, x3 and x4 are nearly I1. Just at different rates do they go to unity. All right. These are the 5 different coefficients. So we have an intercept in 4 different coefficients. What I'm going to show in the next figure is that, or the next table, is that we're going to consistently estimate the betas. without specifying whether they're I1 or I0. And we're also going to be able to construct confidence bounds that have the appropriate length for each of these particular terms, whether the data are stationary or whether the errors are homoscedastic or heteroscedastic, and alternative approaches usually can't handle the heteroscedasticity. All right, so we're going to conduct 4 different types of procedures. First one's using the asymptotic distribution. So we have a normal, distribution with a particular variance. We're going to estimate that particular variance, so sigma v hat square, 1 over the degrees of freedom, just the residuals, right? So that's, and I've told you this won't work. The second method is going to use a non-parametric bootstrap. So y star would be x beta hat plus, say, v star. So this is where we bootstrap the residuals. The third method is going to be with a random weighting bootstrap. This is the one that we're proposing. And then the IVX wald test is a method that's pretty popular in the literature that works very well when you have homoscedastic data. All right, so there's a lot of stuff on this table. What we can show is that if you remember that beta naught was equal to 2, beta 1 was a half, beta 2 was 1, beta 3 was 1.5, and beta 4 was -1. So all these methods more or less consistently estimate the parameter. All right, so that part's good. Down below, we're looking at intervals for 95% confidence regions. So these particular values for A, B, C, and D should all be equal to 0.95 theoretically. Now, in the first 2 ones, we have homoscedastic variance. And then the final 4, we have heteroscedastic variance. Now, what I'm going to argue is that mine will work in both scenarios where the other methods will only work in one. Now, if we look at column C, which is the proposed estimator, these confidence regions, which should be 95%, are very close to 95%. And this is for a sample of n equal to 200, relatively small. Now, notice that the other methods, for example, IVX, is fine when we have homoscedastic cases, but struggle when we have heteroscedastic cases. All right, now, this is for a larger sample of 400. What we see is we're pretty much right on the money all the time, whereas the other methods really begin to perform poorly. This one here is not bad. But we can see that ours works whether the data are homoscedastic or heteroscedastic. We consistently estimate the parameters, and we made no assumptions about whether the data are I1 or I0. So if we had made a mistake, because, test statistics are wrong, right? Think about the size of a test. I mean, you're going to be wrong a certain percentage of the time necessarily. And so if we're trying to conduct research on something very important, we know some percentage are going to be wrong, we can make the wrong decision, right? And we want to bypass that sort of issue. Okay, so I got about 10-ish minutes left. So let me talk about the application. So there's a huge literature on trying to predict stock returns, right? And a lot of people, so like Dow Jones, did work where you're looking at regressing Y on X, Y being excess stock return. So like I said, the difference between the return and, say, the return on a risk-free asset like a bond. And so we regress stock returns on lags of financial variables, and then you would get the T statistic, and typically this is 1Y, 1X. You would get the T statistic, and if that T statistic rejected the null that the coefficient was 0, then you would say that this variable can predict stock returns. Now, the problem is that if XT is I1, then the T statistics no longer are standard normals in large samples, and therefore your critical values are wrong, right? And so you may falsely conclude that something is predictable when it's not, and vice versa. right? All right. So the problem with this is lots of papers write these and lots of tests come up with this and different samples, different estimation methods. They're predictable. They're not predictable. This is, and there's all this back and forth and people argue over this. And a lot of papers have been written saying that mine matters, yours doesn't. And I don't want to take a stance on this. I just want to say, well, what if I don't know? And so what can I do? Well, that's the one thing. The second issue here is we often have endogeneity, and we're going to have to see how we transform our models to deal with this. So we got two big problems here. All right. So our predictive regression model is going to look like the following. So let's just have a single X here because that's what the literature does. So I'm going to regress Y on a lag of X because what happened last period, how does this impact today's stock price? Because that's how we're going to want to make money, right? And we're going to say that XT itself is equal to some lag value of XT plus ARU. One of the problems in this literature is that there may be correlation between epsilon t and UT. And if that's the case, then we say that endogeneity exists. And therefore, we have to find some way to control this. Otherwise, our predictors of beta 1 will be biased. And if they're biased, then we may make false conclusions as well. Okay, so this is a little tricky, and I'm going to try to say it not too fast. So most previous research had to assume the data were I0, I1, or near I1, and then act accordingly. What we're going to say is if we linearly project epsilon onto U, right? So we have gamma U plus VT, where VT and U are uncorrelated. Then we can rewrite UT as this. That's from the previous page, right? We can rewrite UT as XT minus rho, XT minus 1. Therefore, delta XT minus 1 minus rho minus 1, XT minus 1 is what UT is. So I can plug that into here, plug that into UT, and then I can replace the epsilon T here with gamma UT, which is this stuff, plus VT. And so that's what I have here. All right, so this is how we're going to do this. So now we have this system of equations, essentially. YT is being regressed on XT minus 1, and the first difference of XT plus VT. And XT will be equal to rho XT minus 1 plus UT. All right, so I can estimate gamma naught, gamma 1, and gamma 2, right, by least squares. And I can estimate rho by least squares. And so what we can see is that we can identify beta 1 via parameters gamma 1, gamma 2, and rho, all which we can estimate. And so we are going to look at the estimate of beta 1 and its confidence value. That's what we're going to do here if we find endogeneity exists. All right, so you can see how we do this, defining ZT as 1, XT minus 1, and the first difference of XT, and gamma is gamma 0, gamma 1, and gamma 2. We can estimate these two models via our weighted estimation method using this omega t thing. And then we can do the bootstrap with xi t times omega t, similar as we did for this particular score function. So the same idea, we show how we can handle endogenous variables in the same setting. We just had to transform it a little bit. All right, so the data is well-used known data. This gets updated all the time. And if you look up Goyle's website, you can go to his website and you can download these data in any given time. These are used all the time. So we have our left side variable, which is monthly excess stock returns. And then we're going to have a bunch of potential predictions that are either stock-related or interest-related variables. And we're going to check whether or not these variables are endogenous. And then if so, then we're going to estimate the models accordingly. If they're not endogenous, we're just going to run the basic models we had from the beginning of the paper. All right. So there's a lot of stock characteristics here. I'm not an expert in finance, but these are all the ones that are commonly used. dividend price ratio, dividend yield, earning price ratio, dividend payout ratio, book to market ratio, net equity expansion. So these are all variables that have been used to try to predict in the past. And so we're going to copy those. And then interest rate related variables, so term spread, default yield spread, inflation, treasury bill, long-term yield, and these have all been used as well. So we're not sort of hypothesizing which ones will or will not matter. We just, let's run them all and see what happens. All right. Now, it's kind of different. You have lots of data. We have monthly data, and you could potentially try to run it over the whole sample. We have years and years of data, but it's pretty hard to believe that the market isn't changing dramatically or isn't changing significantly over time. So lots of people take different regions. Okay, I can predict over this region, but not this region. And it used to be that we believed there was more predictability in earlier periods than later periods. And so we're going to look at 3 different sample periods based on what people have done in the literature. And we're hoping for ones where we at least have 2 or 3 different business cycles. So we're not just predicting something going up or something going down, right? Those predictions are easy when we're all going up or we're all going down. And so we're looking from December 69 to March 87. So Bretton Woods system fell down. We had hyperinflation, large fiscal deficits, big stock market crash. And then from 87 to 2000, it was relatively stable. This is the area that we call the Great Moderation. And there were economists were believing that we sort of just figured out the market, and now we figured it out. And then everything went crazy, say post 9/11. And so we're going to look at these 3 different periods and see, can we predict in some or in others? All right. We're first checking for whether or not the endogeneity exists, whether the correlation between epsilon t and ut. And so what you do here is you run the first regression, you run the second regression, and just look at the correlation between those 2 residuals, right? So specifically, we're looking at the correlation between epsilon t hat and ut hat. That's what and if that correlation is different from 0, then we believe that the endogeneity exists. And so we can see that in different periods, lots of variables appear to be endogenous. Economists generally believe that most things are. And so a lot of these variables are going to be endogenous. And so for each of these cases, say for this particular one, it's endogenous throughout the entire time period. Then we have to regress y on a constant xt minus 1 and delta xt, right? And in the cases where we don't, we can just estimate the beta as is, right? For example, the third variable, we don't have to do any of that. All right, so let's look at each of these 3 cases. What do we have here? So we have the first time period, so 1969 to 1987. So this first column is going to be our particular estimator, and this is the IVX, the popular one in the literature. And so now if the coefficient is different from 0, so this is a 90% confidence bound, this is the 95% confidence bound. And so what we've found here is that these 3 variables, whether you use our approach or you use IVX approach, all point to predictability, right? The differences occurred. This is, well, one's 90%, the other one's not. This is similar, I would argue, but we believe that inflation does not lead to prediction here. So that's the difference between our setting and the other setting, all right? Now, in the period 1987 to 2000, there's no evidence of prediction at all. And this is what an economist would sort of say, well, that's what I thought would happen. The markets are efficient and these kind of things. This is when things were a lot more moderate, right? And then in the final time period, we find predictability again. It turns out that both models believe that LTY leads to prediction. Our model shows it also for TBL. And so here's where we're gaining, right? If everybody else thought only this one and we saw this one, then that's where, if we're right, then this is where we make our money because nobody else is using this as a predictor, right? So that's the basic story here. Now, I would suggest if you were actually trying to make money off this, thinking about this a little more carefully. But what we've done is we've shown that there is some level of predictability, and we tend to do a good job without making these assumptions from the beginning, right? And that, to me, is the main benefit here, is you're not forcing the user or the computer to make a decision, because the cost of being wrong could be really big. If you tell your boss this predictor is going to predict stock prices and they throw a vast amount of money in that and you're wrong, then we get fired, not to mention we lose a lot of money. And so that's what's sort of happening here. And it's not as if our method is necessarily going to be right, but it's not going to be wrong because we made the wrong choice, right? And so I think that's sort of the big idea here. So to wrap this up real quick, we have this unified approach for both estimation and inference, where we don't have to make assumptions about the order of integration. We propose this method, provide the asymptotics on it, propose a bootstrap method, and show that that works as well. The simulations appear to work well. The asset return stuff is interesting, at least to those who were in this particular field, I would think. And we're also able to address issues of endogeneity at the same time. And not only that, we can do multiple X's, which a lot of these areas cannot. So I think I'm roughly on time, maybe a minute or two late, but I'm happy to take any and all questions at this point.
Thank you, Dr. Henderson. I'd like to encourage everyone to post their questions in the Q&A chat box. Most of our attendees are graduate students. Thank you for your presentation. Do you have any suggestions on what would be an open question related to this work?
Yeah, this is tricky. So I've been really thinking about a lot of these problems lately. And so my default is usually what happens when we have repeated measures. So we can be interested, this sort of approach is very useful if you're looking at a single stock, right? Or if you're looking at the S&P 500 or something along these lines. I think that what would be interesting is if you had a set of stocks, right? And so suppose we have, if S&P 500 is mostly being driven by the top like 5 or 6 stocks right now, so a bunch of tech companies and whatnot, what if we can do several of those, right? Now that we're doing several of them, then the problems become more complicated. You're not going to have, the rows are going to differ not only amongst the X's, but also over the firms. And sometimes we want to put them together to try to have more information, but it's going to be a difficult task, I think.
Okay, and then correct me if I'm wrong, but like the main novelty of your approach is introducing the random epsilon into is that correct?
Or equation, yeah. So it's introduced. So it's not as if these things didn't exist. So doing weighted estimation exists, using this omegas existed. Using a weighted bootstrap exists. So these are things that exist in the literature, but have been underutilized and haven't been used in this setting. So what we're really saying is, look, if you do weighted estimation, you don't have to make these decisions about something being I1 or I0. And people have been struggling with this for a very long time. It's just, we said, hey, there's this technique. If you use it, then you're good, right? And so it's a relatively simple trick, but almost all my research is a relatively simple trick. But it ends up being quite useful. And I think that's what we're really doing here.
And maybe I just missed it or it went over me, but can you give some insights into why introduction of that random variable in the weighting works?
Yeah, so this is relatively technical, but let me try to think of something simple. So if you think about a random walk sort of, can bounce all over the place. right? And sometimes it can get a little bit out of hand. And whereas opposed if you have a stationary model, it just sort of goes about its business and we can estimate things quite easier. Sometimes something will get too large is essentially what's happening. And that is causing, it's like an outlier effect. And so that outlier sort of pulls the regression line, if you will, and it will cause the coefficient to sort of get biased in order to try to minimize that squared residual. And so we're going to downweight some of those observations a little bit so that they don't, you're trying to quiet the loudest person in the room a little bit, right? Sometimes the loudest person in the room moves the discussion. It's that sort of story. We try to tone that person down so that they're not driving the discussion.
Okay, thank you. We also have some questions from the audience. Dr. Utko asks, do you think that the application you explained may face regulatory issues when applied in different regions of the world? I mean, in terms of data usage or technology, etc.
Ooh, so I'm not a regulatory expert. So we'll start with that. I'm an econometrician. Is there some, well, I mean, so suppose I owned a hedge fund, right? I think that's sort of the question. I assume the hedge fund people probably don't care at first, right? And then you wait for somebody to see you making a bunch of money and then they look into you. I don't see any reason why, this would be different from whatever they're doing. They take these very complicated models and they can find a little bit of a gain and then they make it. I don't think we're using vast amounts of data here. I mean, what I've done is relatively simple. It's just least squares. We're not doing really high-powered things. I don't think there is an unfair advantage with respect to computing power or data or something like this. I think this is a relatively simple approach, but like I said, I'm not a regulator. I don't know what they would say here. I do know somebody who did work in one of these big firms. I can bug him and ask him whether or not he thinks this would flag anything. So, but from what he told me, he said what really matters is things need to be based on sound economic principles. Here, I'm not convinced I'm doing that, right? Here, I'm just saying, well, I don't know, therefore I'm gonna skirt the issue.
Okay. And then an anonymous attendee asks, if we have multiple stocks, would there be a model for each stock, or are the models that are able are the models able to handle multiple stocks at once? Is the sliding window for different stocks and using a common model a better approach?
All right, so this is sort of two questions. The first one is more or less what I mentioned earlier, right? Suppose you want to have a set of stocks. You want to look at the first 5 or 6 firms in S&P 500. So I don't know the answer to how to do that right now. I think that would be a nice follow-up, right? So this is one idea I'd perhaps like to do. It gets tricky because how many parameters can we share and how many parameters are going to differ? It could be that for tech stocks it works one way, and then for other stocks it works differently. It could be, for example, Apple works one way, Facebook works, or Meta works another. There are assumptions you're going to make, and those assumptions, if true, are going to help you, and if they're false, then they're going to hurt you. It's the same story, right? Now, the second one is there's sliding window for different stocks, and using a common model, a better approach. I really think that this depends upon the type of stock. It depends upon the time period. These are not easy questions to answer, right? And if I knew the answers to these things, I'd probably be very rich. And so what I'm really trying to do is, a lot of my research, especially lately, is there's a lot of assumptions that we make. And I try to figure out what happens if those assumptions are false. What are the consequences of those assumptions? And then how do I propose a way to relax that assumption or find a way around that assumption? And that's really where I'm at the moment. And this is an example of that. And so I try not to, if I know something about that data and I am very sure about something based on economic principles, I incorporate it. Otherwise, I try to avoid as many assumptions as I can.
Okay, and then one last question from me. So since this is regression, I'm assuming there's lots of applications outside of finance. Have you considered, like, what are some other things you could propose?
Yeah, I mean, I'm always surprised at how many other fields, right? So sometimes I teach short courses on time series, and there's a huge number of different fields that I had no idea. So there was one study I was looking at recently, and they looked after the Oklahoma City bombing. So this was years ago. What happened to the rate at which women of childbearing age were having children, right? And so we just looked at this time series over time, and there's some shock then what happens to the what happens over time. It's amazing at how many different fields this works in, right? But it would have to be in areas where we aren't sure whether or not the data are unit roots or not. And that's the really deciding factor. If we know everything's stationary, or if we know everything's a unit root, then this isn't really important, right? Where it really comes into play is where we have debates of whether or not something is a unit root. And if that is a particular field, my guess is a lot of areas, and I'm just not aware of them. I've only realized I do things that I think work in economics, and then they end up having implications outside of economics.
How much data do you need to determine that?
That's always a great question, right? The best answer I ever heard for something like this is, if you have two good data points, you can estimate a linear regression, right? If they're right on the DGP, all you need are two data points, right?
Yeah.
That's the silliest answer, but it's actually not a bad one. I mean, if you're just trying to estimate two parameters, you can estimate an intercept and the slope. We all learned this in like 8th grade, right? So where can we feel confident? Those simulations we had, the parameters were estimated pretty quickly, right? With 200 observations. Now, if you have a data set smaller than that, you may want to run something. The nice thing about the good and the bad about time series is the time series gets longer, you get the consistency happens, but as the time series gets longer, the chance of some structural break is going to increase. And so there's really this back and forth of what's the ideal amount. And the same thing I tell the students is plot the data, look at it. If you see something funky, look into it. And then, I mean, I don't know if this is very scientific, Google and see what happened to this stock on this day, right? I mean, that's what I would sort of do. And then go from there.
Okay. Well, thank you. We're approaching 12 o'clock. So well, we appreciate the presentation contributing to our distinguished webinar for the Center for Cybersecurity. You'll receive a plaque from the center and a certificate signed by our dean in appreciation for giving your talk today. And hopefully we stay in touch and maybe work and find some way to apply this to cyber and AI.
I'm always open to new ideas. So expanding out of my field is always fun.
Thank you.
All right. Thanks a lot. I appreciate it.
Bye.